Hi, I am Madhurima Choudhury. I am working as a PhD student in my final year with Dr. Abhirup Datta in Indian Institute of Technology, Indore, India. So I'll be talking today about a method to extract the 21 centimeter global signal using artificial neural networks. Another observable quantity in 21 centimeter experiments is the differential brightness temperature delta Tb. So this delta Tb is essentially a measure of a contrast between the CMB temperature and the spin temperature. Based on this particular contrast, we get to observe the signal either as an absorption or emission with respect to the CMB. So there are various current and upcoming experiments like EDGES, SARAS, Bighorn, Sci-Hi, LIDAR, RAGE, MWA, LOFAR, GMRT, HERA, and SKA. Most of these experiments, they target to either observe this 21 centimeter signal as a sky average global signal or as a power spectrum. So as this particular signal is extremely faint, there are observational challenges. The foregrounds, primarily consisting of galactic and extragalactic foregrounds, which are dominated by synchrotron radiation, is one of the major challenges. It needs to be characterized and removed very well in order to get the signal. Our Earth's ionosphere also introduces direction dependent effects by distorting the signal, and we have man made interference, radio frequency interference RFI. To add to all of this, the instrument response changes with observation time, and that also affects the signal to a great extent. All these together makes the extraction process very difficult. So what we do in our work is we construct mock observations and implement artificial neural networks to extract the 21 centimeter signal parameters. So I'll briefly tell you about the training, validation, and testing process methods which we use. So basically, this is the structure of a neural network. We have input neurons. All these circles are the neurons. We have input layers, output layers, one or more than one hidden layers. Now each of the neurons are connected to the neurons in the next layer by a connection associated with a bias and a weight. And the input is passed on through these layers and we get one output y1. So this feed-forward process, at the end of this so-called feed-forward process, in a supervised learning method, we usually compare this particular output with the known original output, and a error function is computed at the end of one pass. The errors are then back propagated, and this process is repeated over and over again until and unless the error or the cost function is optimized. So to quickly show you, we usually have a data set. We split it into training and testing data sets, and then the training process begins, in which a chunk of the training set is kept aside for as a validation set. The network is trained on the rest of the data, and then it's validated using that chunk. Now this chunk is randomly chosen several number of times, and this process is also repeated until we get an optimum performance from the network. Once this testing and training and validation is done, there's a test set on which it is tested to see how well the network predicts. So once all these processes are done, we have a model saved which we can use for some totally unknown data. So what we do is, here's a flowchart. We construct the training data sets like this. We have simulated 21 centimeter global signals. We have modeled foregrounds and instrument response, which we together combine to form the training data set. Then we train our network and we get the predicted parameters. So for test sets, in addition to the global signal foregrounds and instrument response, we also add thermal noise. So in our first work, we have used a TANH parameterized model global signal. We have used the ARIES code, Accelerated Reionization Error Simulations code, to generate such signals. In this model, we have these three parameters: the Lyman alpha background JZ, the ionized fraction of hydrogen Xi, and Tz, which is the temperature of the IgM. Each of these three parameters are modeled as TANH functions like this. So in turn, they are a function of Aref, Z0, and delta C. So we train our neural network in such a way so that it predicts each of these individual parameters, the ref, the Z0, and the delta Z for each of these three parameters. So we first generate the global signals. Then we have model foreground. A typical foreground model is often taken to be a log polynomial in a log polynomial form. So we have four foreground parameters: a0, a1, a2, a3. We vary these foreground parameters as well to generate foregrounds. So we have the signal, we have the foregrounds, and now we move on to the instrument. We follow the DARE radiometer calibration memo by Bradley in 2012. In our work, we have considered two very simple models for the instrument. Basically, the instrument response is given by this kind of a gain function G nu, which is 1 minus gamma square. This gamma square is an antenna reflection coefficient. This antenna reflection coefficient can be modeled by using several sinusoids. So we have taken only two instances. In one, we have taken only one sinusoid, and in the other, which we call the moderate instrument, we have taken two sinusoids. So we have chosen these values of parameters in such a way such that the instrument response will mimic the shape of a band shape. So we construct training sets which look like this. We take the global signals, add the foregrounds which we have generated using our models, and the top one shows us the case where the no instrument response is added, or we can say that it's a perfect instrument case. On the other panel, you can see that we have added instrument effect, and this is how the training set would look like. So from this data set, we predict the tonnage parameters. So once training, testing, and everything is done, we construct the test sets in which we add a thermal noise corresponding to an observation time nt given by this, and we get the predictions for each of the parameters from a set of around 90 samples which we have generated in the test set. So we compute a normalized RMSE, which is used as a metric. We'll get a measure of how well our predictions are. So in our case, when we have taken these randomly chosen 90 samples with thermal noise, observation time corresponding to 1,000 hours, we see that the RMSEs are pretty low, giving us an accuracy of around 93 to 98%. So this was all fine for a proof of concept paper. Next, okay, one more thing which we had done was that we had compared the effect of varying levels of thermal noise. We have increased the thermal noise level from 100 to 500 to 1000 hours of observation, and we've seen that how the prediction would change, like as expected. When the observation time is around 1000 hours, it gives us the least residual. This residual is computed as a difference between the original 21 centimeter global signal and the signal which we reconstruct using the predicted parameters from the neural network. So the reported detection from the edges experiment was very exciting. We found that the detected signal had a very deep and flat absorption trough. Now, what could possibly cause such a deep and flat absorption trough is a question that we all want to know. So we have found that there are two possible explanations. One is that this T background is usually taken to be the CMB only. The background temperature could be a much larger quantity. That is, in addition to the CMB, there could be an excess radio background, which would be contributing to this background radiation. So in such a case, we would get such a large absorption trough. Or our spin temperature could be lower than expected and the IgM could be cooler. Possible dark matter baryon interactions are some of the explanations which would explain why how the spin temperature would be lower than what we already expect. So in our work, what we have done is we have built training sets which will include such edges like sample signals as well, with a very deep absorption trough. So in our work, we have incorporated the excess radio model. The basics of the model are very simple as per as Forlan-Nato et al. 2006. We have modeled the kinetic gas temperature, the X-ray photons, X-ray luminosities, and the X-ray heating terms as per as Forlan-Nato et al. Then we have introduced an excess radio model according to Gurkhan et al. And Chatterjee et al. 2018, where we have assumed that the early galaxies produce radio frequency radiation whose strength is proportional to the star formation rate. And the total background temperature becomes, in addition to the CMB temperature, this excess radio background. So the parameters which get into our code are these F star, F escape, FXH, FX, FR corresponding to the excess radio background, and N alpha. So we vary these parameters to generate several realizations of the global signal. You can see in these two plots, the left hand side are the traditional set of 21 centimeter global signals in which we have turned off the excess radio background, and in the right hand side set we have edges like set of 21 centimeter global signal with the excess radio background turned on. So, uh, so when we train we train a neural network using this particular set of signals, both 1 and 2, and we predict the parameters. We see that now we choose the metric to be an R2 score, which will give us a measure of how well our predictions are from their true values. So we see that the R2 scores varies between 3.37 to 97%. So this is in the case where we have estimated individual parameters. So to improve the R2 scores, what we did was, because the parameters are having correlation among themselves, we combine these two correlated parameters f star fsk and fx fxh, and we train the network to predict these four parameters. These two products of parameters, and N alpha and FR as usual. So now we see that the accuracy shoots up to around 96% and 93-94%. So this is all fine when we don't have the foregrounds added, or you can also think it in such a way that we have removed the foregrounds perfectly and we are giving only the signal to the network. So when we add foregrounds, we model the foregrounds now by the physically motivated models as per Baumann-Rogers foreground model 2018. And this is the combined training set where we have the normal traditional signals as well as the global edges like signals. So with this we add the foregrounds, and our training set looks like this. So when we train our neural network using this training dataset, we see that the individual parameters give us we compute the R2 scores for the test set, in which we have introduced thermal noise in addition to the global signal and foregrounds. And we see that the R2 scores are varying between 70 to 65 is the least one for FSK, 65%, to FR is around 73%, N alpha is 89%, FX is 81%, and so on. So these are, closer to 1 gives a better measure. You can say that it's a better prediction. So over here we can say that our model has an accuracy of predicting the parameters individually, which ranges between 65 to 89%. So after the training, validating and testing the model with this foreground plus signal scenario, we since we have data which is an observation, we put that observation into our network. We take the data from the edges data, the total observed sky brightness temperature, and we put it into the network to see what are the estimated parameters which are predicted by the network. So these are the values of the parameters which we get. So we have f star, f escape, fx, and N alpha and fr with these values. So using these particular values of the predicted parameters, we try and reconstruct the signal. So you can see over here, this blue curve is the reconstructed signal by our model. It does not mimic the shape of the signal as such, because it's a very simplistic model which has not taken into account several things which might be able to mimic the flatness of this signature. But we see that it has been able to pretty well predict the depth of the signal or the depth of the absorption trough. So we can say that a strong radio background could possibly explain the large tip of the edges quite well if taken. So that's all. So we can say that ML algorithms, especially artificial neural network, could be an efficient technique to complement other techniques of parameter estimation. A large number of parameters can be simultaneously predicted, and we can fit for both the foreground and the signal parameters with a very simple network architecture. It's computationally very efficient and utilizes a relevant and realistic training data set. And we could predict astrophysical parameters which has high levels of correlations with quite a good accuracy, but we might be able to achieve better accuracy by implementing more robust techniques maybe. So this information could be used in future works to forecast parameters from mock data sets as well. So thanks. If you have any questions, please ask on the Slack channel or drop an email. Thank you.